So here we have a sealed jar of water, which is the prototypical fluid that I'll be referring back to many times during this course. Before I jump into density, I first want to talk about what makes something a fluid. A fluid is a substance that continually and smoothly deforms when shear stress is applied to it. What exactly does that mean? Fluids flow when acted on by a force, just like water flows downhill when acted on by gravity. That's it. In common usage, we tend to think of fluids and liquids as synonyms, but in science they're not. Fluids encompass more than just liquids, but also gases, as well as something called plasma. We won't talk any more about plasma, but liquids and gases share many of the same physical properties, which are governed by the same laws. So except at times I state otherwise, everything I talk about in this lesson and this course as a whole applies to both liquids and gases. Now let's talk density. I'm sure all of you have some idea what density means. It's a measure of how much stuff is squeezed into how large a space. For example, a steel bar is very dense, while styrofoam is not. When it comes to fluids, there are a number of properties that determine their density. You'll notice that the universal symbol for density is this round lowercase p that's actually the Greek letter rho. The first property that determines density is the mass of the fluid's constituent atoms or molecules. In general, the greater the molecular mass, the more dense the substance is. Remember that despite its appearance to the contrary, water is not some homogeneous uniform substance down to the smallest of scales. Rather, it's composed of individual molecules, each containing one oxygen atom and two hydrogen atoms. These molecules are moving every which way, some faster, some slower. Interestingly, the fact that water is a liquid at room temperature, and thus relatively dense for a fluid, is a bit of a fluke. After all, its relative molecular mass of 18 is higher than many gases, such as 16 for oxygen and 15 for nitrogen, which have densities that are much, much lower. The reason water is a liquid and why it's relatively dense is the large contribution of something called intermolecular forces, including something called hydrogen bonds, that may sound vaguely familiar from high school chemistry. Intermolecular forces are essentially electromagnetic interactions between adjacent molecules or between adjacent parts of the same molecule that aren't strong enough to be considered a true chemical bond. Other determinants of density include the presence of dissolved compounds, as dissolving something like salt or sugar in water tends to impact the mass of the liquid much more than it changes its volume. Temperature also impacts density, with higher temperatures leading to lower densities and lower temperatures leading to higher ones. And finally, there's pressure. For gases, higher pressure leads to higher densities, which might seem obvious when you think about it. Very importantly, however, elementary fluid mechanics assumes that liquids are non-compressible. That is, pressure does not affect the density of liquids. In reality, that isn't exactly true, but the effect is so small that unless pressures are truly enormous, it can be ignored. What range exists for the densities of commonly encountered fluids? Since temperature and pressure can impact fluid density, as just discussed, technically the temperature and pressure should be defined when discussing a substance's density. We commonly refer to something called standard temperature and pressure, or STP. This is defined as 0 degrees Celsius and a pressure of 100 kilopascals. Don't worry yet about what a kilopascal is. We'll get to it in a few videos. So at standard temperature and pressure, the density of water is 1,000 kilograms per cubic meter, which sounds really high until you realize that a cubic meter is actually quite a bit of space. That's the same volume as 500 2-liter bottles of soda, and that's going to be pretty heavy. And if you're thinking what a convenient coincidence it is for water's density to be such a nice round number, it's not a coincidence at all. The unit of measurement of a kilogram is actually defined based on the density of water, which results in a relationship that's critical to remember. 1 liter of water is 1 kilogram in mass by definition. Another commonly encountered fluid is oxygen. The density of oxygen is tiny, 1.43 kilograms per cubic meter. And finally, at the other end of the density spectrum is the densest of all liquids, mercury, at a whopping 13,500 kilograms per cubic meter. The density of mercury is largely a consequence of its atomic mass of 200. The explanation as to why something as dense as mercury is a liquid and not a solid requires quantum physics, and thus I won't get into it here. So how does one calculate density? The equation is one of the easiest to remember and understand in all of physics. Density, which is usually expressed as kilograms per cubic meter, is equal to the mass of a fluid over its volume. Very intuitive. And you may already know that the above calculation also happens to be true for solids. Let's do a super simple example. Suppose the jar shown here weighs 0.2 kilograms when empty and currently weighs 1.4 kilograms. What volume of water does it currently hold? As I just said, density equals mass divided by volume. Plug in the numbers. 1000 equals 1.4 minus 0.2 divided by V for volume. Solving for V, we get a volume of 0.0012 cubic meters, which is equal to 1.2 liters. Moving on from density, let's discuss the concept of specific gravity. Specific gravity refers to the ratio of the density of a substance compared to that of water. Mathematically, this means specific gravity, often abbreviated capital S, capital G, equals the density of the liquid divided by the density of water. Yet another super easy equation. So if the density of ethanol is 789 kilograms per cubic meter, what is its specific gravity? 789 divided by 1000 is 0.789. It's so simple it seems silly for someone to have bothered defining the concept. One important aspect of specific gravity, however, that may seem obvious is that liquids with a specific gravity less than 1 float above water, and those with a specific gravity greater than 1 sink beneath water. According to legend, discovered it while getting into a bathtub, states that any object, wholly or partially immersed in fluid, is buoyed up by a force equal to the weight of the fluid displaced by the object. What exactly does this mean? Imagine a glass or tank of water into which some object is fully submerged. One of the two major forces acting on that object is the force of gravity, pulling it downward, which we call its weight. You may recall from classical mechanics that the weight of an object is equal to its mass times little g, which is equal to the acceleration due to gravity as measured at the surface of the Earth. The other major force acting on the object is its buoyancy, or the buoyant force, which pushes it upwards. The buoyant force is equal to the density of the fluid times the volume of the fluid displaced by the object times g. Whether or not an object sinks or floats depends upon the balance between weight and buoyancy. Neutral buoyancy is a special situation in which an object's density is equal to the density of the displaced fluid. In other words, its weight is equal to the buoyant force. As you might expect, in this circumstance, the object may seem to hover within the fluid. Let's look at an example of using buoyancy to solve a physical problem. What acceleration will a completely submerged object experience if its density is 3 times that of the fluid into which it is submerged? So density of the object equals 3 times density fluid. From classical mechanics, we know that the sum of the forces acting on an object will be equal to the mass of the object times its acceleration due to those forces. The forces here are its weight, which will be partially counterbalanced by its buoyancy. As previously stated, the weight of the object is its mass times g, and the buoyancy is the density of the fluid times the volume of displaced fluid, in this case the same as the volume of the object times g. We know from the last lesson on density that the density of an object is equal to the mass divided by its volume. So therefore, the mass of an object is equal to the density times volume. And remember that the density of this object is 3 times the density of the fluid. So for each mass of the object, we can substitute 3 times density of fluid times volume of object, which results in this. The density of the fluid is present in every term, so it cancels out, and the volume of the object also cancels out. This leaves us with 3g minus g equals 3 times the acceleration of the object. Solving for a, we find that it's 2/3 g. And of course, g is a constant that's equal to 9.8 meters per second squared, which results in an acceleration of 6.5 meters per second squared. This solution is interesting because it highlights that the acceleration of a submerged object is only dependent upon the relative densities between the fluid and object, and is independent of the object's mass and volume. Let's look at another example. Imagine we have an open wooden crate floating on the water, and for some reason we want to put our collection of Michelangelo's David replicas into it. How many 2 kilogram David replicas can be placed into the open 30-liter crate that it itself is 10 kilograms in mass without the crate sinking? The first thing to realize is that each statue that is added to the crate will lead to the crate riding lower and lower in the water. The crate will sink once the water reaches its lip, so the maximum displaced volume of water before sinking occurs is equal to the total volume of the crate. Another way to look at this is to say that the weight of the crate plus that of the maximum number of statues equals the weight of the maximum volume of displaced water. So the weight of the crate is the mass of the crate times g. The weight of the statues is n, where n represents the maximum number of statues times the mass of each individual statue times g. And the weight of the maximum displaced water is the density of water times the full volume of the crate times g. As happens with many buoyancy problems, g cancels out. Now let's enter in the specific numbers. The mass of the crate is 10 kilograms. The mass of each statue is 2 kilograms. While we could calculate the product of the density of water and the volume in terms of cubic meters in order to get the water's mass, we could also use an important relationship from the last lesson. The mass of 1 liter of water is 1 kilogram. Therefore, the mass of 30 liters of water is 30 kilograms. Solving for n, we find that n is equal to 10. So with 10 statues added, the water level will reach the lip of the crate. In reality, since the water probably would not be perfectly still, some water would creep into the crate here and there, and once a little water had gone over the edge, the weight of the crate and its contents would increase, pushing it further down, resulting in an exponential increase in water accumulation until it sank within a very short time frame. So realize, even if the math tells us our crate boat can handle 10 statues, you would not attempt that in real life. So what is pressure? Pressure is a measure of how concentrated a force is. Mathematically, it's represented as force divided by the surface area through which the force is acting. Let's look at two situations. In the first, a 50 kilogram weight is resting on a table. In the second, a 50 kilogram weight is resting on a small wooden block of negligible mass, which is then resting on a table. The force on the table caused by the object's weight is 50 kilograms times 9.8 meters per second squared, or 490 newtons. This will be the same in both situations. However, in the left side example, that force is distributed to the table over the relatively large surface area of the bottom surface of the weight itself, and thus the pressure on the table will be relatively low. While in the right-hand example, the force is distributed through the much smaller surface area of the block, and thus the pressure on the table will be relatively high. In fluid mechanics, instead of one solid object imparting pressure against another solid object, we have a fluid imparting pressure against a solid. But the concept of a force per unit area is the same. When talking about fluids, there are a number of different types of pressure that one can discuss. The most fundamental and important of these is something called the hydrostatic pressure. This is the pressure present within the fluid when it's at rest. It acts equally in all directions, and it acts at a right angle to any surface that is in contact with the fluid. So if we have a glass of water, at a given level within the water, the hydrostatic pressure, which is a result of the weight of fluid above it, acts on the side of the glass equally in all directions. Since pressure is the force divided by area, if the pressure was somehow unequal, it would mean the forces on the glass were unequal, which would consequently result in the glass of water moving. And of course we know that a glass of water at rest does not start to slide laterally on its own. As another example of this, imagine taking a playing card and submerging it vertically into the water. The hydrostatic pressure in the water will act at a right angle to any surface in contact with the fluid. That means that there is a right-sided pressure pushing on the left side of the card and a left-sided pressure pushing on the right side of the card. As these forces are equal, the card will not spontaneously move in either direction. Keep in mind, however, that just because there is no net lateral force on the card caused by the hydrostatic pressure does not mean there is no net force of any kind on it. From the last lesson, we know that there is still the card's weight and the card's buoyancy. So unless the card is exactly the same density as water, it will still move either up or down within the water once released. Is there any way to quantify the hydrostatic pressure? Common experience might tell us that the pressure in fluid increases at increasing depth. For example, when you jump into a deep swimming pool, if you've ever dived deep down underwater, you've probably felt the pressure increasing as you go down deeper and deeper. Quantitatively, this pressure increase can be calculated with this equation. The difference in pressure between 2 points is equal to the density of the fluid times little g times the difference in vertical height between the 2 points. In the case of the glass of water here, if we were interested in the pressure at the bottom, the 2 points we would use would be its bottom and top. The pressure at the top is equal to atmospheric pressure, and the difference in vertical height is just the depth of the water. To refer back to the last lesson on Archimedes' principle and buoyancy, some of you might realize that the buoyant force on a submerged object, which we said was equal to density of the fluid times volume of the displaced fluid times g, is simply a manifestation of the difference in hydrostatic pressure that's acting upwards on the bottom side of the object and the hydrostatic pressure that's acting downwards on the top side of the object. An interesting consequence of this hydrostatic pressure equation, which may or may not be immediately obvious, is that the pressure at any given depth is independent of the shape of the container or the path that the pressure must be transmitted along. For example, I could have a collection of rare and exotic jellyfish that I want to display in my home, but to highlight their uniqueness, maybe I want to build an equally unique aquarium system in which to house them. If I wanted to know what the maximum water pressure was at the bottom of the system of tanks, the only thing that would matter is the total vertical distance between the top and bottom. The shape of the tanks, the volume of the tanks, the width and length of the connecting tubes are all irrelevant. Also notice that the lower tank needs a sealed lid. If the lid was not there, the weight of the water in the upper tank would cause the lower tank to overflow. This is an example of a principle frequently paraphrased that fluids at rest seek their own level. This means that the surface of any fluid at rest will have the same height above the surface of the Earth at all points. Let's look at a quantitative real-world example of hydrostatic pressure. We have a house at the bottom of a hill, which gets its water supply from an open, unpressurized water tank at the top of the hill. The water tank is 4 meters high and full, and the base of the tank is 50 meters above the level of the house's faucet. Given these distances, what is the house's water pressure? As we just reviewed, the pressure difference between 2 points within a fluid system is the density of the fluid times g times the total difference in height between those 2 points. So we have the water pressure in the house's faucet minus the water pressure at the very top of the tank, which if the tank is open and unpressurized, is equal to atmospheric pressure. This equals 1,000 kilograms per cubic meter times 9.8 meters per second squared times the total height of 54 meters. This is equal to 5.29 times 10 to the 5th kilograms per meters second squared plus atmospheric pressure. The units of kilogram per meter second squared is cumbersome to talk about, so this combination has been defined as its own unit, something called the Pascal, after the French mathematician Pascal, whose name has been attached to a specific physical principle that will be the subject of a future lesson. In addition, this idea of a pressure that is equal to some number plus atmospheric pressure gave rise to the concept of gauge pressure, since atmospheric pressure is essentially equal at both the top and bottom of this type of system. The gauge pressure in this type of situation is the total pressure minus atmospheric pressure. When people refer to the term pressure in most everyday situations, such as discussing their home's water pressure, whether or not they realize it, the gauge pressure is often to what they are actually referring. Pressure, applied anywhere to an enclosed body of fluid, is transmitted within that fluid equally in all directions. This is an extension from lesson number 3 on hydrostatic pressure. Explaining it further will be much easier with a few examples. First, imagine we have a wooden barrel full of water. A vertical tube is inserted into the lid. If the maximum pressure the barrel can hold is 100,000 pascals, how high must the column of water be in order for the barrel to rupture? We know that the primary equation of hydrostatics is the pressure gradient is equal to the density of the fluid times acceleration due to gravity times h. In this case, when we talk about the maximum pressure the barrel can hold, it actually refers to the maximum pressure gradient. In other words, the pressure inside can be no more than 100,000 pascals greater than that outside, which is presumably atmospheric pressure. 100,000 pascals is not an atypical value for a wooden barrel. Let's then plug in the numbers. 100,000 pascals equals 1,000 kilograms per cubic meter times 9.8 meters per second squared. Solve for h and we find that it's 10.2 meters. That's right, if the total height of the barrel and the tube is more than 10.2 meters, the barrel will rupture. This may seem quite surprisingly low, even more so once you realize that our solution did not need to involve the diameter of the tube, and thus the diameter is irrelevant. So the tube, which can be 1 centimeter wide or smaller, and contain a total of less than a liter of water, can still generate enough pressure to rupture a barrel. It's quite counterintuitive, yet nevertheless true, and it's because of Pascal's law. The pressure created by the vertical tube, even if that tube is tiny in size, is still transmitted through the fluid equally in all directions, including out to the walls of the barrel. According to legend, this specific example was actually devised by Pascal, and he used his experience with it to formulate his law, though the story is probably not actually true. Let's look at another example. From lesson 3, we discussed a glass of water in which the pressure at the bottom could be calculated from the hydrostatics equation, where the pressure gradient is the difference between the pressure at the bottom and atmospheric, leaving this solution. What if, instead of the top of the glass being exposed to atmospheric pressure, we replace it with a piston that pushes down on the water with some force? In this case, the atmospheric pressure gets replaced with the pressure of the piston. If you recall, pressure equals force divided by surface area, so the piston pressure equals the force divided by the surface area of the piston, which, assuming it is a perfect circle, is equal to pi r squared, and we end up with an analogous solution. You may not immediately realize it, but this solution depends upon the fluid being non-compressible, which we said was an assumption made for liquids in elementary fluid mechanics, though this would not hold true for gases. If the glass below the piston was filled with a compressible gas, the density of the gas would be a function of the pressure applied to it, and our solution would look a bit more complicated. But let's apply this general concept of a piston imparting a force on a non-compressible liquid in a somewhat more complex situation. Imagine we have a system of 2 pistons of markedly different sizes attached by a liquid-filled tube. There is some force pushing down on piston 1, which has a radius of 2 centimeters, and resting on piston 2, which has a radius of 10 centimeters, is a 500 kilogram weight. Inside the pistons and tube, instead of water, we'll have some type of oil. Given the radii of the 2 pistons, what is the minimum force that is needed to be applied to piston 1 in order for the weight on piston 2 to be held up against gravity? So the force of gravity due to the 500 kilogram weight must be equal in magnitude to the force imparted on piston 2 by pressure in the fluid. Since pressure equals force divided by area, we know that the pressure in piston 1 equals the force of piston 1 divided by the area of piston 1. The same relationship holds true for piston 2. The key principle to solving this problem is to recognize that the pressure in piston 1 must equal the pressure in piston 2 as a consequence of Pascal's law. Remember, a pressure applied anywhere to an enclosed body of fluid is transmitted within that fluid equally in all directions. So the pressure that the force from piston 1 imparts within the fluid inside piston 1 is transmitted through the connecting tube to the liquid in piston number 2. So we know that the force on piston 1 divided by the area of piston 1 equals force on piston 2 divided by the area of piston 2. And the force on piston 2 is equal to the force of gravity on the 500 kilogram weight, so we can substitute that in and solve for force piston 1. Force of gravity is mass times g, and our areas are pi r squared. And if we plug in the numbers, we get a total force of 196 newtons. That's the same force that a 20 kilogram weight has as a consequence of gravity. So the force that you would need to generate in order to lift a 20 kilogram weight, if directed onto piston 1, would be enough to hold up a 500 kilogram weight sitting on piston 2. As with the barrel example, this seems counterintuitive, yet it's true. This type of system of multiple pistons of varying sizes, connected by fluid-filled tubes, is known as hydraulics, which are used in an extremely diverse variety of machines that we encounter in everyday life, most notably the automobile. Round pipe that serves as the conduit for some liquid, and suppose it varies its size along its course. The fluid here is moving left to right. Fluid flow is defined as the volume of fluid that moves past a certain point per unit time. It is mathematically represented as Q, which for some reason stands for flow, and equals volume divided by time. This is a powerful relationship in itself, but it also leads directly to the focus of this video. We'll take an arbitrarily long section of narrow pipe here, and we'll define the cross-sectional area as area 1 and the length of the section as L1. From what we have just learned, Q1, or the flow of fluid through this segment, will be equal to the volume divided by time. We know that the volume of a cylinder is equal to the cross-sectional area times its height, or in this case, V1 equals A1 times L1. That seems straightforward enough, but look, we can group these a little differently, and length divided by time is a velocity. So this results in the flow through section 1 is equal to the cross-sectional area of section 1 times the velocity of fluid moving through section 1. With identical analysis, if we define a section 2 in the wide part of the pipe, we will quickly determine that Q2 is equal to area 2 times velocity 2. The key realization here is that the flow in section 1, that is how much volume passes through section 1 per unit time, must be equal to the flow in section 2. If these were not equal, fluid would back up somewhere and become very compressed, and this would violate the assumption of elementary fluid mechanics that liquids are non-compressible. So if Q1 equals Q2, then we can say the product of A1 and V1 is equal to that of A2 and V2. This is what's referred to as the continuity equation. This is the simplified form appropriate for non-compressible liquids. You can think of it as a statement of conservation of flow, which is really the law of conservation of mass as applied to moving fluids. That is, what passes through section 1 must pass through section 2. Volume of fluid isn't lost or created somewhere in between the two. Compressible fluids also have a continuity equation, but it's a bit more cumbersome and with few applications outside of physics and engineering. Let's do two examples. Suppose we have a fire hydrant and we hook up a fire hose and turn it on. The radius of the outlet of the hydrant is 2 centimeters and water is passing through it at 4 meters per second. The radius of the nozzle is 1 centimeter. Given all of that, what will be the velocity of water as it exits the nozzle? Sounds like a continuity equation problem, so we'll start with area 1 times velocity 1 equals area 2 times velocity 2. The areas are pi r squared. Substitute in our known values and pi cancels. This leaves us with a velocity of 16 meters per second. We started with a fluid conduit of variable cross-sectional area in which some non-compressible liquid was traveling left to right. And we looked at how the product of the cross-sectional area and the velocity in one segment must be equal to the product of the cross-sectional area and the velocity in another segment. For the Bernoulli equation, we're not directly interested in the cross-sectional area in each segment anymore, but rather the velocities, the pressure, and the height of the fluid above some arbitrary zero level. In the interest of time, I'll spare you its derivation and just give the Bernoulli equation to you. The pressure at point 1 plus 1/2 the fluid density times the velocity at point 1 squared plus the density times little g times the height at point 1 must equal the sum of those same values at point 2. Or another conceptually identical version states that this sum is a constant. This equation may look a little unwieldy until you realize that just as the continuity equation is nothing more than the law of conservation of mass as applied to fluids, the Bernoulli equation is the law of conservation of mechanical energy applied to fluids. This term is the potential energy density of the fluid. This term is the kinetic energy density of the fluid. And this term is something called pressure energy density. Don't worry if the term pressure energy is totally unfamiliar to you. Just know that as a liquid travels through a conduit, these various energies trade off at different points, but their sum is always the same. For the rest of the video, I'll go through two rather different examples of how to apply the Bernoulli equation. First, imagine we have a bucket on top of a marble block. If a hole is drilled at the bottom of a full bucket of water, whose height is h, what velocity will the water have when it initially exits the hole? This problem may seem unexpected at first, since a bucket of seemingly stationary water looks quite different than the conduit I referred to a second ago. However, the water in the bucket is not stationary after all, and the bucket is just an unusually shaped conduit. Let's start by writing out the full Bernoulli equation. Next, we need to define a point 1 and a point 2. One of these will obviously be the exit hole, and the other should be a location where we know the most information. In this case, it's the top of the barrel at the water line. So there are points 1 and 2, which makes this velocity v2. So how can we substitute in for the missing variables? First, the pressure at point 1 is atmospheric pressure. What is the velocity at point 1? By the continuity equation, the velocity times cross-sectional area at point 1 must equal the velocity times cross-sectional area at point 2. However, if we assume that the cross-sectional area of the entire barrel is much, much larger than that of the hole, the velocity at point 1, that is how fast the water line is moving down, is very, very small, and for practical purposes can be assumed to be 0. The value of y1 is the height of point 1 above some arbitrary level. We can make that arbitrary level anything, but let's make it the top of the marble block. So y1 becomes h. Next we have p2. This may or may not seem intuitive, but if point 2 is located just at the lip of the exit hole, the water here is also exposed to atmospheric pressure. So p2 is also p atmosphere. v2 is of course what we are solving for, and y2, or the height of point 2 above the top of the marble block, is 0. So p atmosphere cancels out, and this term is 0, as is this one. This gives us density times little g times h equals 1/2 density times v2 squared. Densities cancel, and solving for v2, we find that it is equal to the square root of 2 times little g times h. There are a number of fascinating things about this rather elegant solution. First, the velocity of the fluid coming out is independent of its density. Whether it's water or mercury, the velocity will be the same. Next, the width of the barrel and the width of the hole are both irrelevant, provided that the barrel is many times larger than the hole. Finally, and most interestingly, this is the same velocity that an object or fluid would have as it passed point 2 if dropped from an h and allowed to fall straight down under the influence of just gravity. This is historical trivia, but this solution is called Torricelli's theorem. Torricelli is the 17th century Italian physicist who invented the barometer and for whom the unit of torr is named after. Let's look at another application of the Bernoulli equation, one that's a bit more complicated. Here's a schematic of an interesting contraption called a Venturi Meter. It consists of a horizontal tube of two different widths, where a vertical tube is attached to both the wide section and narrow section. A fluid moves along its length. You've probably already noticed something interesting. The height of the vertical columns of fluid are not equal. This might seem to be a violation of the principle discussed in the lesson on hydrostatics, that fluids always seek their own level, but that only strictly applies to stationary fluids. This is an example of the Venturi effect in which the pressure in a fluid moving through a conduit is decreased when the fluid flows through a constricted section. The term Venturi effect is also occasionally used more broadly for a variety of related phenomenon, particularly in medicine. How could we analyze this situation quantitatively? Suppose we can measure the height difference between the two columns, which we will call h. Given only A1, A2, and h, what is V1 and V2? I can imagine this seeming like a profoundly difficult problem, but I guarantee you that we have already covered all of the tools necessary to solve it within this video series. So let's start with a complete Bernoulli equation. We see that although the pressures, that is P1 and P2, are neither given to us nor requested as part of the solution, we'll still need to include them along the way. The first simplifying step is to realize that the vertical height of the two sections is the same, so these terms cancel out. With a little rearrangement of the remaining terms, we are left with P1 minus P2 equals 1/2 the density velocity 2 squared minus half density velocity 1 squared. Factoring out the 1/2 in density gives us this, which is looking more manageable. But where do we go from here? The first trick is to realize that in order to get rid of the unknown P1 and P2, we will need to use our knowledge of hydrostatics, and we'll need to define, at least temporarily, a different height, that is the height from the center of the main horizontal conduit to the top of the lower of the two vertical fluid columns. I'm going to call this H prime. How does defining H prime help? We know from hydrostatics that the hydrostatic pressure is density times little g times the height of the overlying fluid. So P1 is equal to density times little g times the sum of h and h prime. The same rationale allows us to state that P2 is equal to density times little g times h prime. And a simple but nevertheless cool algebraic trick allows us to simply subtract one equation from the other, giving us this. P1 minus P2 equals density times g times h. And we can substitute that right in here. The next major trick to achieving the solution to this problem is to remember the continuity equation. A1 times V1 equals A2 times V2. Solve for V2 and substitute that in here. And with these two substitutions, we are left with this. Density cancels, and everything that is left is either given or is what we are solving for. At this point, we leave physics behind and concentrate just on the algebra. Multiply both sides of the equation by 2, factor out the V1 squared, and solve for V1. To arrive at an expression for V2, substitute all of this back into the continuity equation. This answer might initially look ugly and cumbersome, but I actually find it kind of awesome that the velocity of fluid moving through this tube can be determined from the ratio of the cross-sectional areas and the difference in column height. From studying electricity and magnetism, while some of you may not. I'll review it briefly here. Ohm's law for electricity simply states that the voltage as measured in volts equals current as measured in amperes times resistance measured in a unit called ohms. This is usually abbreviated V equals IR. Here is a simple circuit. The battery, represented by 4 lines of alternating length, provides the voltage. The resistor is represented by a zigzag, which interrupts the normal unimpeded current, represented by I, as it travels clockwise, starting and ending at the battery. An extremely simple Ohm's law problem might give us the voltage of the battery, suppose it's 12 volts, and the value of the resistor could be 4 ohms, which is frequently represented by the Greek letter omega, and we could be asked to solve for the amount of current traveling through the circuit. So 12 volts equals current times 4 ohms, and the current is 3 amperes, usually shortened to amps. It's very straightforward. But how do we apply the same concept to fluids? In fluids, voltage, which is the difference in electrical potential in electricity and magnetism, is replaced by the difference in pressure between 2 points. Current, which is nothing more than the flow of charge, is replaced by fluid flow, and resistance is left as resistance. It's the concept of viscosity. Imagine we have a straight tube or pipe, and it's filled with water moving left to right. The water, of course, is made up of tiny molecules of H2O, and while the net motion of the molecules on average is in a certain direction, individual molecules don't flow in a smooth, coordinated way. Instead, various intermolecular forces between neighboring molecules are causing some pushing and some pulling this way and that, resulting in an internal friction within the fluid. Viscosity, which is usually denoted by lowercase mu, is a measure of a fluid's resistance to flow and deformation by stress due to this internal friction. It approximates the common notion of thickness. For example, water seems inherently thin as far as fluids go, and that's the consequence of a relatively low viscosity. While maple syrup, or even more so molasses, is very thick and has a very high viscosity. Viscosity is dependent upon temperature, but essentially independent of pressure. The first part of this statement may seem obvious to anyone who cooks a lot. Sauces, for example, seem to become thinner as they heat up in a pan and thicker as they cool down. Viscosity becomes a critical component of the relationship between a pressure gradient along the length of a tube and that tube's length and radius. And here is that relationship. For a tube with length L and radius R, the pressure gradient in a fluid as measured between 2 points along a tube is equal to 8 times the viscosity of the fluid times the length of distance between the points times the rate of fluid flow, all divided by pi times the radius to the 4th power. This is known as Posis Law. If we remember that the pressure gradient equals flow times resistance, we can quickly derive a corollary to Posis Law, which is more important in medicine than the law itself. The resistance of fluid to flow is equal to 8 times viscosity times L divided by pi times radius to the 4th. The dramatic feature of this relationship, as we'll see in a moment, is that 4th power. While length has a modest role in determining the resistance in a tube or resistance in a blood vessel, the radius is much more important. Small changes in radius can result in dramatic changes in resistance. Turbulence. In common usage, it typically refers to something like abrupt shaking of an airplane in flight, which you may have experienced at some point. Perhaps you've been kayaking or whitewater rafting and have used the word turbulent to describe a fast-moving stretch of river that looks particularly treacherous. But is there a slightly more precise way we can think about it? To further our understanding, we'll need to contrast it with something called laminar flow. So I'm going to have this tube represent a stretch of pipe carrying some form of fluid. It could be anything from water to crude oil to chocolate syrup. In laminar flow, the movement of this fluid through the pipe is very orderly, with all of the fluid particles moving in a straight line along its length and without any lateral mixing. For complicated reasons well beyond the scope of this video, the flow is always faster in the middle of the pipe and slower as one moves closer to the sides. Engineers really like laminar flow because when a fluid is moving in this neat, organized manner, the classical laws of fluid mechanics hold true, and the reactions of the fluid to minor changes in the system are very predictable. For the most part, the physical laws presented in the preceding videos in this series assume fluid is moving with laminar flow. In contrast, in turbulent flow, while the overall net motion of the mass of fluid may still be forward, the motion of individual particles within the fluid is highly chaotic. We can see all sorts of eddies and vortices develop, and as a consequence of this complicated transition between states, some of the classical laws of physics no longer hold true. When studying or designing physical systems that involve fluids, it's critical to be able to predict which of these two types of flow will be present. A dimensionless value called the Reynolds number is the single best predictor of this. Unfortunately, there is not one single symbol or abbreviation for the Reynolds number that is used uniformly across all applications. I'll label it RE, which is probably the most common, though I've also seen R sub E, N sub R, and even a fancy script R on occasion. It's named after the 19th century physicist Osborne Reynolds, who wasn't the first to describe the concept, but was the first to heavily focus on it and popularize it. The basic idea is that the type of flow is determined by the ratio of the inertial effects to the viscous effects of the fluid. Most of you probably know that inertia is that fundamental physical property by which an object at rest tends to stay at rest, and an object in motion tends to stay in motion. In fluid mechanics, however, due to boundary effects and nonlinearity, and other scary sounding terms, internal inertia within the fluid leads to turbulent flow. You are also probably familiar with the term viscosity, which is a quantitative number to describe how thick a fluid is. When I think of the viscosity of a fluid, I imagine holding a cup of it and trying to stir it with a spoon. The easier it is to stir, the lower the viscosity. So pure water has a relatively low viscosity, while hot fudge has an exceptionally high viscosity. Viscosity promotes laminar flow. From this, one can see that at higher Reynolds numbers, inertial forces will predominate and the flow will be turbulent, while at lower Reynolds numbers, viscous forces predominate and the flow will be laminar. The next questions you might have are, first, is there a simple equation to calculate the Reynolds number? And second, is there a specific cutoff value that distinguishes laminar flow from turbulent flow? Unfortunately, there isn't just one equation for the Reynolds number, nor one specific cutoff. Because it's applied in so many completely different situations, it must take different forms in each. After all, Reynolds numbers don't just apply only to fluids moving through a tube, but also to a submarine traveling through the ocean and an airplane wing flying through the air. Each situation gets a different form of the equation and a different range of numbers that predict probable laminar flow versus probable viscous flow. However, the most appropriate form for this discussion looks like this. Reynolds number for a liquid traveling through a pipe or vessel equals the density of the fluid times its velocity times the diameter of the pipe or vessel divided by the viscosity. Unless you're a mechanical engineer, you'll never need to actually calculate the Reynolds number, so memorizing this equation isn't terribly important. However, understanding it conceptually is. If higher Reynolds numbers increase the chance of turbulence, then we can predict what specific changes in the physical parameters of a fluid flowing through a pipe increase the chance of turbulence. Those will be a higher velocity, higher diameter, higher density, and lower viscosity. For example, water passing through a garden hose is more likely to be turbulent if the valve is fully open, giving it a high velocity, as opposed to only partially open with a lower velocity. And there will be less likely to be turbulence if the water is replaced with molasses. When it comes to successfully applying the concept of Reynolds number to medicine, one important point is realizing the increased Reynolds number from an increase in the diameter of a tube depends upon the velocity remaining constant. However, when dealing with a tube of varying diameter along its length, such as a blood vessel, this does not hold true. You may remember the continuity equation from lesson 6. This stated that the cross-sectional area of the tube at one location times the velocity of flow at that location equals the cross-sectional area of the tube at a second location times the velocity of flow there. Thus, within the same tube, as the diameter increases, the velocity decreases and vice versa. Furthermore, the degree of velocity change is to the square of the diameter change. As a consequence, within a single tube, if the diameter decreases along its length, the risk of turbulence at that location actually increases. I can imagine that may have been a little confusing, so here's another way to reach the same conclusion. We know that flow, abbreviated Q, is equal to the velocity of fluid times the cross-sectional area of the tube it's traveling through. Assuming the tube is perfectly round, its cross-sectional area is equal to pi times the radius squared, or if we are using diameter, 1/2 d squared. If we divide both sides of the equation by the area term, we get this expression for the velocity. and we can substitute this into the Reynolds number equation. Since we're only interested in the qualitative relationships, we'll ignore the constants, yielding this. For a fluid flowing through a circular tube of varying diameter, the Reynolds number and chance of turbulence is proportional to the density times flow divided by the diameter times viscosity. This is the equation from this video that warrants memorization. So what now? How does this relate to medicine? When fluid movement turns from smooth laminar flow into chaotic turbulent flow, all of those eddies and vortices transform a small amount of kinetic energy in the water molecules into sound waves. Whether or not we realize it, we see examples of surface tension every day as it manifests in a wide array of common physical phenomena. One such example is how we can take a bowl, fill it with water, and float a piece of paper on top, despite the paper's density being greater than that of the liquid. Although this would seem to violate the principle of buoyancy, as discussed in Lesson 2, it's something that everyone has observed at some point. Another example of surface tension is the tendency of water to form spherical drops instead of a continuous stream when flowing from a faucet at a relatively slow rate. The drops aren't perfectly spherical on Earth because of the effects of gravity and air resistance. However, water droplets in space, where these are not factors, do form perfect spheres. Here's another example. A small puddle of water on a flat horizontal surface. Although it would seem that water should collect in puddles, that's only because it conforms to our common experience, not because it makes intuitive physical sense based on most people's knowledge of physics. Suppose if all we knew about the puddle is that it is composed of countless individual molecules of H2O, and gravity is pulling each of those downward to the lowest possible level, and if water as a liquid freely flows based on the forces that are acting on it. If this was the extent of our knowledge of water, we would logically conclude that the puddle would continue to spread out in all directions until it had reached a depth of a single water molecule. That way, each individual molecule would have obtained its state of lowest mechanical potential energy. Of course, this doesn't happen, but why doesn't it? It's the consequence of the intermolecular forces that were first mentioned in Lesson 10 on viscosity. Although some of these forces are sometimes pulling and sometimes pushing molecules around, overall, there's a net electromagnetic attraction occurring between adjacent molecules in most liquids. This attraction pulls the liquid together until an equilibrium is reached with other forces, in this case gravity. Surface tension is a measure of the contractive tendency that allows liquids to resist deformation by external force. For example, if we take this puddle and we very carefully place a paperclip on top of it, the paperclip imparts a force created by its weight on the surface of the water. This force pushes down on the surface, and this deformation of the water surface pushes apart the water molecules underneath the paperclip ever so slightly. If the sum of all of the attractive forces between the disrupted molecules is greater than the paperclip's weight, the clip will rest on the surface of the water. This is not a consequence of buoyancy, but rather of surface tension. Of course, our experience tells us that this only works for objects which are very light. In addition, surface tension is dependent upon properties of the liquid, the solid or liquid with which it interfaces, and temperature. Surface tension relates to physiology. It's important to describe something called the law of Laplace. Imagine a hollow sphere made of some form of pliant material, like plastic, for example, and inside is a thin layer of water coating the inner surface. The scale of this thin layer is greatly exaggerated in this picture, but the layer of water is made up of individual water molecules, all of which are attracting each other. The net sum of the circumferential attraction is that the water is actually being pulled inward. If there was no enclosed gas, the water would contract down into a ball. However, if there is enclosed gas, the result is an increase in the pressure of that gas. The surface tension pulls the water inward until an equilibrium is reached with the pressure pushing outward. The law of Laplace relates the surface tension to the enclosed pressure. It states that the pressure inside the spherical bubble is equal to 2 times the tension divided by the radius.